counting significant figures without having any rules to memorize? Yes, you heard that right. And our approach is to focus on the definition of significant figures. Significant figures, as you may remember from the previous video, is all the certain digits in a measurement plus exactly one uncertain digit. So when we count significant figures, we're really interpreting from whoever made that measurement, how many digits are they certain of, plus that additional one guessed that digit. Our approach is to start with the first non-zero digit and then continue counting all the other measured digits in that measurement. Let's do a couple examples to illustrate this approach. 12 milliliters. We know the 1 is significant because it's the first non-zero digit. The 2 is also significant because it's intentionally written down. So we have a total of 2 significant figures. 12.0 milliliters, though, we know the 1 and 2, once again, are significant. Here, though, we encounter a 0 at the end of a number. Zeros can be a little bit tricky, but we can determine whether they're significant or not by using what's called the cover-up test. We're simply going to cover up that 0 with a finger, perhaps, and decide, does the value of the measurement change with that questionable 0 covered up? So we have 12 milliliters versus 12.0 milliliters. They both have the same meaning, which means that that 0 is a certain digit, that 0 is intentionally written down, so therefore it's significant. Third example is 0.0030 meters. We start the first non-zero digit. Once again, we run into another 0 at the end of the measurement, so we cover it up. 0.003 meters versus 0.0030 meters. They both have the same mathematical meanings, which means that it's also significant. So a total of 2 significant figures. Part D is a measurement in scientific notation. With scientific notation, we approach it the same way. So we have the 1, 2, 3, 4, for a total of 4 significant figures. Notice that in scientific notation, we ignore, for the purposes of counting significant figures, we ignore where the exponent might be. And then we'll finish up here with example E. We have 580 grams. We know the 5 is significant, and we know the 8 is also significant. Once again, we have a 0 at the end of the number. What do we do with it? Well, let's use a cover-up test. 580 grams with the 0 not covered up, 58 grams with the 0 covered up. So it fails the cover-up test. So unlike examples B and C, we can't definitely say that this 0 is significant, but we also can't definitely say that this 0 is not significant. Unless we made a measurement, we really don't know whether that 0 is supposed to be significant or supposed to be not significant. It's an ambiguous situation. It may be that the person who made the measurement is confident that the value of the measurement is 580 something, and they're guessing, in this case, the ones place. If that's the case, then we would have 3 significant figures. Or it may be that they're confident that the value of the measurement is 500 something, and they're guessing in the tens place, which means this 0 would be not significant. Consequently, we only have 2 significant figures. And this matters, this ambiguity matters, because, as we talked about in the previous video, the more significant figures we have in a measurement, the more confidence we can have in that measurement itself. So if I run into a situation where I have an ambiguous case as to how many significant figures there are, it's best to rewrite the measurement using scientific notation. So if I want to correctly imply that I have 3 significant figures, so this situation, it's best to write this correctly as 5.80 times 10 to the second grams. Or if I want to correctly imply that this 0 is not significant, then it's better to write as 5.8 times 10 to the second grams. When we talk about significant figures, the first thing that comes to mind is error in measurements. There's always error attached to measurements. When we do calculations involving measurements, then necessarily implies that there's error also in the results of those calculations. What we'll spend the next couple of videos on is focusing on how to properly express where that uncertainty is when we do calculations involving measurements. See you then.